Hello, welcome back. So let's move to practical stuff. So the previous videos we introduced the problem, what we're going to do, general introduction also to the foundations of optimization that cut out any black box solver. In this case, we're using OpenFOAM. So now let's do the first case. So remember that what we're going to do is that we have this geometry. We have parameterized this geometry using 4 points with basically a curve, and everything is generated in geometry mesh using Salome. Here we have our general loop, and in the first case we're going to use gradient-based optimization. In particular, we're going to use this method, the method feasible direction. Remember that in gradient-based we need to formulate a problem. Okay, so sit down, understand what you're doing, and so on. So let's work in this case. So I will run here, and if you are using our Windows Assistant Linux no image, you will have everything there, but in any case you have in the video description where to download the files. But let me go here, and you should have this data structure there, and you see that we have many cases. We're going to work each one of this one, but we're going to focus in gradient-based optimization. Okay, so here you have the classical files, okay, the workflow. So we have the input file of Dakota, then the simulator, the script. Always you are going to find a readme file, so just read. Sometimes I put some comments there. Here you have the solution, so I already run here, but you have the table out. You have the whole trace of OpenFOAM, just the table out of Dakota, and then here you have the template file. Remember, this is the files that are going to be parameterized. So let me address this. Okay, remember you need as well the case base, the one that you know that is always working. So we have a case here, it's always working, I'm not going to run. But just to show you what is happening here is that we generated the geometry using Salome. In Salome, you can parameterize things and you can write a Python script. So this is a script. Okay, everything is done. I'm not going into details here. This requires another video. Probably if I receive enough votes, I can show how to do this, but it's very straightforward. Okay, so basically what we're doing here is that these are our variables, the points that I'm controlling. Okay, and these here later I'm going to parameterize. This is what Dakota is going to change. Just to show you that in the template there, so this is the base case, it's working. You have the instructions there how to run it, but the parametrical variable here in the templates is this script. And look at that, it's very easy to parameterize. So now we're not anymore like in the cavity case that we were in the OpenFOAM dictionaries. Now it's something else, okay? So remember that you can parameterize anything in theory. So see, by just adding curly braces, the name of the variables, you are able to parameterize. So by changing this one, we're going to get different shapes. So namely, this is what we're going to do. So change these points and then get this, and well, we force this case, and this is our optimal solution. So let's see how things work. So now we know what is our parametric variable. So at this point, let's move and run. So I reminded also of what we're doing here. Let me go here. So we need to formulate the problem. We have our design vector. We need to compute a quantity or many quantities of interest. In this case is drag. These are the 4 points. You need to also give linear and nonlinear constraints. Our linear constraint will be the size of our domain, okay, how big and how large you want to be this design vector, but also you can add nonlinear constraints. So in this case, we're not adding nonlinear constraints, but let's see, I will do another video just to show you how to do it. That because that nonlinear constraint is a quantity that you need to compute. It's not a design variable. It will be like a quantity of interest. So for instance, can be the area of that shape. So you need to multiply the coordinates or whatever. So somehow you need to compute that. So it's relative, it's not a big deal. So our general optimization loop, the most general one is that you have your optimization tool, can be any tool, in this case Dakota, then that tool needs to generate some input parameters to your black box tool, and then your black box tool will generate an output that needs to be post-processed and render not useful for the optimization tool. So in the specific of this case, it will be something like this that we're working. We'll already visit this when we're going to do our loop there. So now let me go And look at the specific in Dakota. So we have Dakota, the input file. We can run everything sequentially or concurrent. We're going to see how to do that. Dakota is going to generate a parameter file. This parameter file will be the input for our simulation script here, our black box solver. So here there is a filter. So this information that Dakota is generating that by no means can be digested by Salome or by open needs to be filtered, substitute into the script. So namely will be this. This is the filter that we're applying. So in Dakota is a utility called the prepro, but you can implement any utility to do that. So we filter that one, we substitute files, we run. Then when we run the solver, we're going to get an output that needs to be filtered again in the specific format that Dakota likes. And then it keeps looping. And let me talk about that specific format. And now I'm going to go here into documentation. It's very important. Dakota documentation is excellent, so I invite you to read it, get familiar with methods and so on. But what is important is this, the Dakota result file. Okay, the specific one that I'm talking here, this output filter, because it's not like you're going to get any output from the solver and then Dakota will understand what is it. You need to format that in the format that Dakota likes. So that specific format is like this. So here we have Dakota result file format, and Dakota likes this file in this format. So first you will have here your response functions followed by, your objective functions or calibration terms, then followed by nonlinear inequalities, followed by nonlinear equalities, followed by gradient, followed by hessians. Usually here we don't know gradients and hessians. So usually CFD, that information is computed numerically, but as you're doing, let's say toy cases where you have your function, you can give that information as well here if you want to compute it. But we're going to limit just to the first one, that will be objective function, quantity of interest, and nonlinear inequalities equality if you have them. So this file needs to be in this very specific format. First quantity, second quantity, third quantity, and so on as you have them. So in this case, it will be a very simple text file. Let me show you that usually I put there to deal with that in our base case. I put a dummy file, and that format needs to be something like that. So in this case, if you have, for instance, three quantity of interest or one quantity of interest, the linear constraints needs to be like this. So in our case, we have only one, you put one. So remember that the software that you're going to use will give you information, so you need to post-process to put it like that. As you see, it's super, super simple. And that's the most important thing that you need to know at this point. So now we're ready to run. So let me close here, and I will go to the directory grad. Remember that we're using OpenFOAM 11, so let me load the variable. Also, the Dakota version that I'm using is the latest one, if I would recall, 6.18. So at this point in theory, we're ready to run, but let's revisit what we're doing. And remember that we're also using gradient-based methods, so you need to formulate your problem. And just to mention something here that in documentation also study types. For instance, you go into optimization, see that developers of Dakota also talk about, okay, this is your problem. You need to formulate it. You need to know what you're doing. So they give you here some general theory. So take your time, read the documentation. Very interesting here in the index, I think it will be here, keyword reference. As you go into methods, you have all the methods, keywords that you need to add, and so on. So in this case, we're going to use this method, MFD, well, not this one. We're going to use the conmin this one. So if you click there, you will have a reference, so you can check the literature and so on. And you have here all the keywords that you need to define. So that being said, let's open files. So the first one that I need to open, so you have a case base. We know that it's running, already tested, and that is your first step. Be sure that to have a starting point that is always working. Now I go Dakota case in, and this is the simulator script that how things work. And also I have template. These are the template files. So let me put it also there, right? Template file. And let's see step by step what is going to happen here. So hopefully here you're going to understand better because it's a little bit more complicated workflow that we have. So the environment entry, remember that here we save the output of the optimization task here in this file. So you can give it any name here. You have different entries, so visit the documentations to know the entries there. Then the method here, you define your method. So see that, for instance, let me use starting one, this one. So you have your method there. You have here I define a max iterations, convergence tolerance. If you don't find anything, it will take default values. So as you go here, you will see that everything is optional. So meaning that there are some default values. You enter here, you will see what will be the values. So if you want to know all those entries, just visit documentation. So in theory, it's just enough to pick up a method, a gradient-based method. These entries to do advanced stuff, most of the time single is okay. Variables. So here you define your variables. So remember in our problem, we have 4 design variables. So here continuous design variables. You can also have discrete variables and so on. So for us, continuous is okay. You have a starting point for those design variables. So this is our starting point. And see that I put in some comments here. So in this case, mentioning that if I start from here, it's like in CFD, the closer you are to that final solution, the faster that convergence would be. So starting from here, you have a slow convergence to solution. Instead, if you kind of go closer to that solution and you go away from this, let's say, ideal symmetric shape, you will exhibit the problem, the optimization loop will exhibit a faster convergence. So small details like that you can play around with this case that is very affordable. Then you have upper and lower bounds. So this will be our linear constraints, our dimension size of of our domain. So x1 is limited between this and this, this and this, this and this, and so on. So if you don't put anything, it will be an infinite domain. So it makes no sense because then the optimization tool will try to use on very large values that you need. So usually you know your problem, you know what will be those upper and lower bounds, and you define those there. Give it a name, and pretty much these are your variables that then you can use into your template. So we have a template that, remember, that is located here, template there. And this is basically what will happen, that Dakota will search into this file, and then it will substitute, will find these curly braces and the name of the variable. And just to reiterate this, that I already checked, but in using OpenFOAM, Dakota, many other tools, you don't have any problems using curly brace name of the variables. You don't find the same notation. But if that is the case, that you can get a conflict between variables, you can change this delimiter. So again, go to your documentation and you can find how to do it there. But I have to be honest, I have used many tools, ParaView, many Python libraries, APIs. I never found any conflict with this curly with this notation, curly brace name of the variable. Should also, you need to put also some the name of the variables. Try not to use something that you know will be used in that library. But I think never had happened to me that it will change something in your library. Any case, you have that. So we keep reading here the variables. Then we pass to the interface. The interface is how we link applications. So we're going to use fork. There are many ways to do it. Fork interfaces, I think it's the best one. So we use the fork interface. Then asynchronous means that we can run simulations at the same time. So here we put asynchronous, and then you have this entry. Remember, you have documentation, and you can give a maximum of evaluation concurrency. So here we're telling that you can run 4 tasks at the same time, or you can put 400. In this case, you can put 400, but it is not going to run all those function evaluation, because remember, this case, when you are doing gradients, they are limited to the maximum number of variables. So the maximum that you can do is 4 variables plus the objective function. So at most you can do 5 or 11 if you're using center difference to compute the gradients, because you need 2 points. So here, let's say, let me put 10, but it's not going to change anything. This is our script, the sequential steps. Dakota is going to generate this file. This is all the parameters that Dakota generate to do your experiments. So this is the filter that I mentioned in the slides. Okay, so you have here, you have a filter. It is filtering that parameter file because again, format that Salome or OpenFOAM doesn't understand. Then Dakota will expect a file with this name, and it has this specific format. Remember, here we talk about in the documentation, it's very important to have that specific format. So in this tutorial, we're going to work with easy cases, so it's just one single line, or at most will be 2, 3, 4 lines, depending on the number of objective functions and nonlinear constraints. So it's very easy to format that. So, but the name must be this one, and this is just save everything in the working directories and so on. So leave your trace. Where do you have the template files? So we have seen that you have this folder and you put all your template files. So in our case, it's this one. And in the end, okay, also the name of the directory and so on. So this is kind of copy and paste. I think I need to update these scripts because they are a little bit old and open, and the code is changing. So for instance, this entry is not needed anymore. So let me erase it so you don't have it. So I need to update a little bit. Then we move to responses, objective functions. So how many objective functions do we have for quantitative interest? We have one. Numerical gradients, sure, because we never know that function in CFD, so they need to be, the gradients need to be approximated numerically. So what method we're going to use? So we use now the source Dakota, it is in charge of that. And here you have some other options, but Dakota is okay most of the time. I would say 99% of the time is Dakota. What type of method you're going to use? So we're going to use forward differences to compute the gradients, but you have the option that to use central. So remember, central needs to function evaluations, forward just one. So here, forward is most of the time it is okay. I have to say, if whatever you're doing is inexpensive, maybe central will be the best option, but most of the time these evaluations are expensive. So go for forward, but there is no problem. It's not like in CFD that like your discretization of the convective term needs to be second order. Here we don't have that requirement. Then you need to have to give a step size, so your gradients when you're evaluating, at least the initial step size, the initial perturbation, let's say, needs to move with some size. So you give some initial size, and then that will be adaptively, the code is going to compute that size. Can be very large, very small, but sometimes, but you need to give this size. So you can play with this, and you will see that, for instance, if you give a very low value or you use the default value, you will see that it will be very, very, very slow, the convergence. Then if you give a larger step size, it will be much faster. If you give something too large, probably it's not going to converge. So these are, let's say, the idiosyncrasies that you have with the grading methods. You need to know something about your case. And for instance, this information, how big or how small this step size needs to be, it is related to knowing something. Then we don't have Hessians, and then you give descents. So we want to minimize. So we know that we're minimizing drag, and pretty much that's all. And let's focus in this file, simulator script, which is this one. So remember, here what you have is the sequential steps how you run your black box tool. So first you have the preprocessing, which is the parameter variable substitution. So basically here what we're doing is this. So we have these files, and see that here we do the substitution. Here we're not doing anything, just to show you that you can do substitutions of many files. So as you go there, input template, basically you're going to have these, okay, the 4 design variables. I think I will use these informations to write some other files, but the most important one is this one, the templates. When you open the template that I already have it here, here's where you're going to do your substitution, and that's all. You're going to, at this point you're going to have that variable, okay, here. And now you move to the analysis. So in the analysis, remember that you're moving files. So you know that you have your case base here that is always working. So just move files from there into your current directory. Remember that also we're working in a given directory, that when we run, you're going to see that. Move files. Here we're renaming this one to profiles 4 points Python script. Then we run using Salome. So in my case, I have Salome installed here. So very important, please give the right path. So in my case, this is the right path. I installed it here. But it's also if you are using our Windows system, Linux machine, you will have it there as well. And this is how you run. Very important as well. The -t means run without the graphical user interface. Just interpret these scripts, and that's all. Then this will save that mesh in a given format. It's UMB, ideas UMB. So this is just to convert the format, then rename some patches and run the solver. Easy peasy. And if you want to run in parallel, just put the compose par and so on. Be careful that you need to have your resources. After you have this, you move into post-processing. And here's where I get that data. So we know we were OpenFOAM user, hopefully. And you know that, for instance, force coefficients and so on, they are safe in this folder. So in this case, I'm using AWK. This is a Linux utility to post-process this data. So here I'm running to a fixed number of iterations. And this is where maybe things can get a little bit tricky. In this is the case, I know that it's enough to have 1,000 iterations to have enough data to do some post-processing, compute mean values, standard deviation, or whatever you want to compute. So here I'm computing that. Save that in this file. Then just doing some bash scripting moves files. And then in the end, I'm going to have this file, which is coef. And this coef file will have all the coefficients. So here I'm using the input information. Recall that I have it at the beginning, just to have the design variables. And here I put everything together and I have my coefficients. So this is a support file. I like to do it because while running some Dakota, it's not going to save everything in that table.out file. That table.out file is safe at the end. So I like to have that information readable, available while running. So I do it like this. There are many ways to get that now, but I like to do it like this, but it will be up to you. And then here's where we at. Remember that these loops, they're automatic and they need to be fail safe. If something happens, you need to be able to keep running. So this is the way how I do it in this case. So see that I know that I need to generate a results.out file. So basically this script is telling that is this results.out file is not empty. If this file is empty, it means that something happened. So if something happened, I will have this dummy file, and this dummy file, it will force the simulations to keep running. So recall that here I have that in the case base, I had that dummy file, that is this one. So basically something bad happens, it's going to take this file and it's going to read just the first one, okay, because you have only one objective function, and it will force to run the case. So this is how we enforce that. Now in Dakota, in the latest version, they added an option failsafe to do that automatically. So let me go, I think it's recover option. So I put here. So it's a very neat option. So you have it there that now you have it automatically, not simulation failure capturing. You have different options here. So the recover one is the one that is going to keep it iterating. You have different options, recover, continuation, and so on. But usually it's important that you need to force, in case that something bad happens, you need to, and if you want to let it run, you need to force it not to run. In this case, it's not the ideal method because I'm putting a value of 1. Likely that value of 1 would be very far from that function evaluation. So it's better to use another method. So another method would be that you know where it failed, and then you choose a value close to that value, but also have to be a little bit different to discourage the optimizer to test again that point, because you know that it is failing that point. So you need to discourage the optimizer to go to that point, but it needs to be close to that point because you are moving in that direction. So there are many techniques to do that. I have to say the implementation in Dakota, it does a very good job. So I need to update this one also to add that one, but this simple case, this is okay. And to show you a little bit how to do some scripting. So this is a case to force it, and if nothing happened, is everything is okay, so is that file is not empty, you have here the step where you have the results out files. That step is here. No, that file exists. Okay, so we have everything. So here's where you have. Now you compute $2, remember, means results, and $1 means the input file. So you have it here, $2, $1. So those are script variables. So basically here, this file TMP text and compute and see the drag coefficient, which I'm interested in. And in this drag coefficient, I have averaged that quantity, and I have here how I do the average and save that in results out. So if that value exists, nothing happens. If this value doesn't exist, it means that my simulation failed somewhere here, something happened, and that will be empty because I'm not going to have this file. So what I'm doing is forcing that. And voila, this is it. This is how we run the case. So now let's launch the case real time. Okay, so to launch that, remember to load OpenFOAM. I already loaded, I think. And then I go Dakota -I, Dakota case, and that's all. Also here, and sometimes I put in the comments about here how to launch the case. So this one, as you put like this complete line, it's going to save the standard output here, and then also if there are errors, it's going to save the errors like that. So this is a standard now also using Dakota. So it is explained in the documentation. So I advise you to use those options to have that trace as well. Might be useful. And if you look at the solutions directory that I'm putting there in some cases, or in some cases, now in every case I put this solution, so it means that I'm using Dakota 619 or OpenFOAM 11. You will see that I always, okay, here I didn't put those files. Okay, I forgot to put it there, but I always like to save that trace. So let's run the case. We're here ready to go. Let me click there, send, and voila. So see that I mentioned that it will create working directories. So when you enter, let me update here. So see that first is evaluating one function. And after evaluating that, you have the solution. It will launch for gradients evaluation, and that's all. It keeps iterating. So see that here, these are running, in a synchronous mode at the same time. So see that now this is another function evaluation, and here as it is moving, it's doing all the computations, getting gradients, determining now what is the best direction to move. But let me enter in one of these directories. So see that all the steps that I put here, simulator is create, you are running those steps sequentially. So when you enter into this file, remember that you are already in this work dir here. And why it is called work dir, let me go here into the Dakota-ins file, is because you give that name here. Okay, you can give whatever name you want. Avoid, by the way, avoid spaces or funny characters because it doesn't like and it will crash. And that is tricky to track, by the way. So if you put like this, it will be tricky to track. But avoid that. So I like to put like underscore if you want to put spaces to make distinction between words and so on. So basically, this is what is happening. You are moving all these files, template dir. So when you look at here, you do your substitution. Everything that you're doing here, you are already inside this directory. So see that you are moving files from this relative location into here. So you are moving the case that you know already works. You are moving files with the boundary conditions. Here also, you know that you already have this profile where you did the substitution. And let me show you that file, this one. And look at that, already Dakota substitute the values there. You don't have any more the curly braces. So Dakota substituting, and then you start to follow all the steps. So here Dakota is running and so on. Something to show you here. I think I need to update this Dakota script. This now will be this one. It's a little bit old. I haven't updated in a while. So Dakota had Salome, sorry, had changed a lot. Talking about Salome here, had changed a lot, and I think it's changing for the good. And as you read this one at the end, I have this entry. Probably some of you already use Salome, knows that Salome is using TCP ports, that stuff, and sometimes those ports are busy. So this is the way that I use to kill the ports. Now, after you open the port, you kill it. But as I mentioned, that I think this is not needed anymore. At least I have done large cases with more than 10,000 evaluations using Salome, and it doesn't crash anymore. So that is very positive. But as you look here, also you have all the steps, how things are done. So the geometry, the mesh, everything can be parameterized. The mesh here is quite good also. It's not easy to use, but it's a good option. And now I'm considering very seriously to use. So at this point, we have a solution. So see that 28 functions evaluations, including gradients evaluations and function evaluations. And now you have a solution here. So always read your output script and you will have everything there. So basically this is going to tell you, okay, what you did, everything where you have the best value. So the best value is here, final optimization information, the value of the objective function, and you have here your vector. But you can have more information if you go here. Remember that we saved that trace. So that trace is here, log. So this one is standard error, so there are no errors, just a warning, so there is no problem. And then you have here your output. As you look at here, you can have the whole trace. So here you will see a lot of stuff here because remember you are running Salome, OpenFOAM, whatever. So you have everything here. So sometimes can be tricky to read, but as you look at the standard output of Dakota, it's very clean. Okay, you don't see all the other steps. So this is what was happening. So evaluation one, remember a starting point, you get this objective function, then we run at the same time for gradients evaluation. So this is a step size, your initial perturbation. So now you can better understand that. So we say that I want that initial perturbation 0.2, and it will do it in every direction. Then it will find the solution of best improvement, and it will move in that solution. Then again, it will compute another gradient and see that now the step size is different. So now it's doing its own magic to get there, and you have there everything. So here it's computing another gradient and keeps going until it gets to the best solution. And here at the very end, let me go here. You have best function evaluation, okay, character here in this point, which is the solution that we want. This is the value, total time, and so on. Important also that here you see in this output, you see 32 evaluations, but when you check the directors, you have 28. So it might happen that sometimes you are repeating some evaluations for some reason. So they actually see that you have 4 duplicates. So those 4 the duplicates evaluation, they are not done again. You have it already saved, and Dakota will use that information. So talking about that information, we have the files, and then you have this RST file. This is the restart file, but in this file also you have all the information of whatever happened here. So in the next video, I'm going to show you how to interrogate that restart file and also how to look for information. So this is also the next step when it comes to failure capturing. So if for some reason your simulation crash, let's say function evaluation 17, that information is safe here. So you can say, okay, restart from this, from the 17 and keep iterating. So you need to do everything from scratch. So this is our like very much this. And also you have all the trace safe there. So now that we have a solution and hopefully you saw that it was quite fast. Let's do some post-processing. So if I go to work dir one, here in this directory, I will have Paraphone. Let me open Paraphone. So see that have the solution there. Be very careful because you have also large cases. This is stuff you can leave a big trace. So look at the mesh, structure mesh, very nice mesh. I didn't put boundary layer. I just another toy case to the so Reynolds though. So I didn't play with that, but you can add the boundary layer in Salome with no problem. And here you have a starting point, and this is the solution that we have. See that we have an unsteady flow, the way it is oscillating, so that can make things a little bit tricky in optimization. We already talked about that when we address foundations, that optimization, when it's unsteady, is not easy, and when you have this case, look at your average solution, don't look at the instantaneous value, because for every single value, you are going to have a different optimal value. So you want a global quantity. So this will be the case. Then, for instance, if I go to work dir 10, you are going to see how things are changing. So in workdir 10, I will launch Paraphone, apply there, and see that now it is squeezing the geometry. Likely here, I think it's the unsteadiness is less because it's becoming more aerodynamic. It's taking that shape of the airfoil. And now if I go, let's say, workdir 18, let's see what happens here. And probably it starts to get that shape, and see that this is the shape that we're talking, and the shape that we mentioned here, this is what is happening. And as I mentioned, that optimization is very subjective. So here we want to minimize drag. If we don't put constraints and we let it as an open problem, the optimal solution will be all these values will be zero with zero surface. But it's not a feasible solution. It's not a realistic solution. We put it like this and we force it to get like to this value. But for instance, if you would like to optimize LD, which is very important in aeronautics, okay, this efficiency factor, this is not the best one. So globally speaking, this one will have the lowest drag, but when we look at another quantity like LD, probably globally speaking, this will be the best one because we'll have a low drag, but also will produce more lift, and even more if you add a little bit more curvature. So formulate your problem. This is part of the problem formulation, and also we create another video just to change and an exercise from this working case how to compute this for LD. And you have the evolution there. We can look at the solution and let's see what happens there. And you have it there. You can look at your pressure field, everything, and all this processing. Also remember that part of you can save your Python scripts and you can save files and do everything, automatically. So there will be another case, will be the most complex workflow that I will show you how to do that, but it's relatively easy. And the final solution usually is the last folder, but you can look at also your trace. So let's see. So here it will tell you in 28. I know best evaluation you have it in folder 24. So let's see, but usually, okay, you have this one, but these are small variations. So I am in 28 and it's telling me that is function evaluation 24 that will correspond to workdir 24. So basically this was the best value, and then you have the other ones that there were small perturbations. Okay, so this should be that one. And there you go. We have our airfoil. And see that this was a large deformation in the mesh when it comes to the mesh. So we started from something large, which was this one, and then we deform the mesh. So here you might say, okay, I want to use mesh morphing. Yeah, mesh morphing has limitations. So in this case, mesh morphing is not the best approach because it will break down sooner than later. So it's better to do the remeshing approach. That usually is the best approach, but it might be a little bit expensive. I think computational resources today, you can do the meshing in parallel, so it's not a big of a deal. And now I look at there at the solution, and voila, you have your solution, everything working smoothly. And as well, now remember that you have all the data structure of OpenFOAM, you have it there. So you can interrogate all your data, you will have your force coefficients there, and so on. So then you can, if you don't understand what was happening in my simulator script here when I was doing the average, you can run, now that you have a solution, you can try and run that script and you will see what I was doing. So let me show you, for instance, the first line. So I'm using this one, but many people will be more comfortable probably using Python. But I think I don't like to overcomplicate things, so this is more than enough. So see that this one is computing this quantity. So basically it is reading this file and using your Unix to get familiar with this AWK, but basically read the records from 808 to 1008. So here I'm running until a fixed number of iterations. So then there are some techniques that, for instance, if you know that fixed number, you need to let it run, and then you need to compute the average, let's say, of the last 100 iterations. So when you see that things are not oscillating anymore, you can stop. So it's up to you to put your logic there. Then here you compute the average, you do everything, and that's all. You get this quantity, and this quantity you save it in a file with this name. But see that in that file with this name, you have this keyword there. So the other part that I'm doing here is that erasing that keyword. So basically now I say take this file and take the column 2 will be this one, and put it in TMP text, and then move TMP text to $2. $2 is resolved. Okay, so why do I like to do this? You might say, okay, but you can save that directly in results, whatever. I like to save now. Sometimes things can get very complicated, so you don't know what is happening in each file. So here I'm putting that keyword. Okay, this is your mean drag. And let me enter into the directory. So you will have all files. So talking about patterns in, this is what Dakota generates. By no means this will be useful in OpenFOAM or Salome or whatever. So this is interpreted. So it's where you have that filter. When you filter that data, it will be filtering into your file already. So that in template. And then all the post-processing that I'm doing is moving these files here. You have all this stuff. But at the end of the day, this is what you need to give to Dakota. And see that it's just a single line with that quantity that you have there. And that's all. As you see, it's relatively easy. It requires no some skills to post-process data, but as soon as you get a complicated cases, I think you will be able to do uh, crazy workflow. And just to show you this coef also, I save it. So here I have all the information there, the quantity of interest, I have leaves, drag, and moment that I can use it for something else. And this is it. Okay, this is how you do optimization, shape optimization using a little bit more complex workflow. And I think this is your starting point to do anything. So from this point, I will work in some other cases, but using different techniques for optimization. Then we move to design space exploration. Let's see if I have time and the willingness to do also a join, but pretty much it works in the same field. Something that I'm really excited as well is that I'm doing also machine learning and putting XGBoost, so the design space exploration. I'm going to show you just how to use XGBoost, but XGBoost, the important thing is that you need the data. So you have the data, you construct your models, and your models will be as accurate as the data you are given. So if that data is garbage, it doesn't matter if you are putting there the best machine learning technique or neural network or whatever you want to call it. It's not going to work because you have garbage. Okay, those AI NL techniques, they're not going to guess anything. They just use what you have, and what you have is bad, your outcome would be rubbish. So that's all for this case. Thank you for your attention, and see you next time. Bye. Okay, by the way, I forgot to mention something. Remember that if you have a case here, you have all the folders. If you want to run another case, remember to clean up these directories. You have all this data, likely Dakota is going to give you problems, so you need to clean up. And here you have this automatic script that is cleaning up everything. So it's going to clean all the trays that you have, but also these tables out, restart files, and so on. So if you type in your terminal, let me show you here, you have Dakota clean out, everything is clean. So do not forget to run another case in the same directory, clean out everything, or you create a new directory, just move the necessary files. Also, something important that I have seen that sometimes happens, that these files that I have here, they need to be executable. It's very important that Dakota case in, okay, this Dakota case in, it will call the simulator script, but this simulator script needs to be executable. And I have seen sometimes there is a problem when you extract files or if you move to another system, that this file is not executable anymore. Also Dakota clean, so you need to have execution rights here. So see that when you look at the properties, you have X there. So to get that one, and in the case that you don't have that, it's quite easy. You can use chmod 755, and then the name of the file, and that one will make it executable. So be careful about that. So that sometimes it might happen. It can be also tricky to track that. So if you are extracting files, moving files to another directory, I have seen that in some system it happens. So yeah, that's all the final warning. And yeah, see you next time. Bye.